Welcome to this episode of the CompTIA Tech Plus Prepcast by baremetalcyber.com. Let's begin. Wireless networking refers to the method of transmitting data between devices without the use of physical cables, relying instead on radio frequency signals. The most widely used wireless technology in computing today is based on the Institute of Electrical and Electronics Engineers 802.11 standard, more commonly known as Wi-Fi. The CompTIA Tech Plus exam includes objectives related to wireless capabilities, including understanding available frequency bands and the types of interference that can affect performance. A solid grasp of wireless standards allows you to design, configure, and maintain networks that deliver both reliable connectivity and security. The 802.11 family of standards defines how wireless local area networks operate and evolve over time. Each version of the standard introduces enhancements in performance, range, and efficiency. Commonly referenced versions include 802.11n, 802.11ac, and 802.11ax, each representing a generational improvement. Modern labeling now uses generation numbers for easier recognition, such as Wi-Fi 4 for N, Wi-Fi 5 for a C, and Wi-Fi 6 for AX. Understanding the capabilities of each generation is critical when selecting equipment and designing network layouts. 802.11n, or Wi-Fi 4, operates in both the 2.4 GHz and 5 GHz frequency bands, offering flexibility in range and performance. Under optimal conditions, it can deliver a maximum theoretical speed of 600 megabits per second. One of its significant innovations was the introduction of multiple input, multiple output technology, which uses multiple antennas to improve throughput and reliability. Despite newer standards being available, Wi-Fi 4 remains in use in many residential and small business environments due to its broad compatibility. 802.11ac, also known as Wi-Fi 5, operates exclusively in the 5 GHz band. It offers a maximum theoretical throughput exceeding 1 gigabit per second, which makes it a strong choice for high-bandwidth applications such as streaming high-definition video. This standard introduced wider channel support, up to 160 MHz, and improved multiple input, multiple output capabilities. While it offers faster speeds and less interference than 2.4 GHz networks, it also has a shorter effective range due to the higher frequency. 802.11ax, branded as Wi-Fi 6, operates in the 2.4 GHz and 5 GHz bands, and in its extended version called Wi-Fi 6E, also in the 6 GHz band. It brings a major efficiency improvement through orthogonal frequency division multiple access, which divides channels into smaller resource units for more efficient handling of multiple devices. This standard is particularly suited to high-density environments such as stadiums and large office complexes. Under optimal conditions, it can reach theoretical speeds exceeding 10 gigabits per second, making it the fastest widely available standard. Wireless networking operates across 3 primary frequency ranges, each with distinct characteristics. The 2.4 GHz band offers longer range and better wall penetration, but is prone to interference from household devices like microwaves and Bluetooth equipment. The 5 GHz band delivers faster speeds and reduced interference, but with a shorter range. The 6 GHz band, introduced with Wi-Fi 6E, provides higher throughput and lower latency, but currently has more limited device support. Selecting the correct frequency for a given use case is essential for performance and reliability. In the 2.4 GHz band, there are only 3 non-overlapping channels, typically channels 1, 6, and 11, which are used to avoid interference. When channels overlap, signals interfere with one another, resulting in reduced performance and unstable connections. The 5 GHz and 6 GHz bands have many more non-overlapping channels, which allows for better throughput and less congestion in busy environments. Proper channel planning is a fundamental step when setting up wireless networks in shared or densely populated areas. Several environmental and technical factors influence wireless performance. Physical barriers such as walls, ceilings, and metal objects can weaken signals or cause them to reflect, leading to dead zones or multipath interference. The distance between a device and the access point plays a significant role in speed and stability, with signal strength dropping off as distance increases. The number of devices connected to an access point can also cause congestion, especially if they are all transmitting data simultaneously. Additionally, background radio frequency noise from other devices can degrade wireless performance. There is a natural trade-off between wireless range and speed, depending on the frequency used. Higher frequencies such as 5 GHz and 6 GHz support faster throughput but cover shorter distances and are less able to penetrate obstacles. Lower frequencies such as 2.4 GHz reach further and penetrate walls better but offer lower maximum speeds. Strategic placement of access points determines how well a network covers its intended space, and in larger areas, signal boosters or mesh network systems can be deployed to eliminate coverage gaps and maintain performance. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Wireless network topologies describe how devices connect and interact in a Wi-Fi environment. Most networks use an infrastructure topology where access points connect to a central router, providing structured communication paths for all wireless clients. An ad hoc topology allows devices to connect directly to each other without an access point, useful for temporary or small-scale setups. Mesh networks employ multiple interconnected access points that route traffic dynamically, ensuring extended coverage and redundancy. The choice of topology affects network performance, fault tolerance, and how easily the network can be scaled or managed. Security in wireless networks is essential to protect data and prevent unauthorized access. Modern Wi-Fi deployments use Wi-Fi Protected Access 2 or Wi-Fi Protected Access 3 encryption to secure connections. Open networks without encryption are vulnerable to interception and malicious activity. Wi-Fi Protected Access 3 offers stronger encryption methods and resistance to brute force attacks. A secure configuration also requires a strong passphrase and the disabling of insecure features such as Wi-Fi Protected Setup, which can be exploited if left active. Device compatibility and roaming behavior are important factors in maintaining a stable wireless environment. Older devices may not support newer Wi-Fi standards or certain frequency bands, which can limit network performance. Dual-band and tri-band routers enable compatibility by serving both legacy and modern devices simultaneously. Roaming capabilities allow a client device to move between access points without dropping the connection, which is crucial in enterprise and large residential deployments. Ensuring compatibility across devices helps maximize performance and minimize connection issues. A wireless site survey is a planning and troubleshooting process that measures signal strength, identifies coverage gaps, and detects interference sources. Tools such as wireless heat maps and spectrum analyzers provide a visual representation of network coverage and performance. Performing a site survey before deployment helps determine optimal access point placement and reduces dead zones. In enterprise and high-density environments, regular surveys ensure that the wireless network continues to meet user demand and adapts to changes in the physical space. Troubleshooting wireless issues requires systematic evaluation of symptoms such as slow speeds, dropped connections, or weak signal strength. Common solutions include repositioning access points, changing channels to avoid interference, and updating firmware. It is also important to verify that encryption settings and authentication methods are correct and compatible with client devices. Restarting affected devices and ensuring network drivers are up to date can resolve many common problems quickly. Comparing wired and wireless performance helps in deciding how to connect specific devices. Wired Ethernet generally offers higher speeds, lower latency, and greater reliability, making it preferable for servers, desktop workstations, and high-demand applications. Wireless connections, however, provide flexibility, easier installation, and mobility for users. In many networks, a hybrid approach is used, where wired connections handle core infrastructure and wireless is reserved for mobile or less critical devices. Wi-Fi extenders and mesh networking systems are two methods used to improve coverage in larger or complex environments. Extenders work by receiving the existing signal from a router and rebroadcasting it to reach farther areas. Mesh systems consist of multiple interconnected access points that share the same network and optimize traffic routing automatically. Mesh networks generally provide better performance and reliability than extenders, especially in buildings with multiple floors or dense wall structures. In wireless networking, device roles and configurations vary depending on the hardware. Routers serve as the central point for traffic management between the local network and the Internet. Access points broadcast the wireless signal to client devices, while wireless controllers manage and configure multiple access points in enterprise networks. Some devices can be configured in different modes, such as bridge, repeater, or dedicated access point, depending on deployment requirements. On the CompT Tech Plus exam, wireless scenarios may test your ability to select the best standard or configuration for a given use case. You may be asked to troubleshoot problems caused by interference, improper band selection, or overlapping channels. Understanding how wireless signals behave, the capabilities of different standards, and the implications of certain configurations is essential to selecting the correct solution. Diagram-based questions may also include access point layouts, channel assignments, or range indicators. Key terms to review for this topic include 802.11n, 802.11ac, 802.11ax, Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, service set identifier, frequency band, channel, mesh, Wi-Fi protected access 2, Wi-Fi protected access 3, and extender. Grouping these terms by speed capability, frequency range, and technology layer helps reinforce the differences and proper use cases. Using flashcards and comparison tables can strengthen recall for the exam. Wireless networking knowledge is applied in many real-world environments. Home users depend on Wi-Fi for all connected devices, from phones and laptops to smart televisions. Businesses require stable coverage for conferencing, collaboration, and secure access to internal resources. Public spaces often use guest access portals, access point zoning, and capacity planning to manage large numbers of simultaneous users. Technicians are responsible for installing, optimizing, and securing wireless systems to ensure performance and reliability across diverse use cases. In the next episode, we will move into Domain 3 on applications and software, beginning with an overview of operating system components. We will explore how file systems, drivers, services, and interfaces work together to support both user interaction and application performance. Join us for Episode 34, Applications and Software Domain Overview. Thanks for listening. Please visit baremetalcyber.com for more cybersecurity information and education, including a new children's series. For more information on books and more, follow us at cyberauthor.me.